So who wants opcat to be included? Who doesn't? And who doesn't know better? Okay, so pro opcat is like 3 people. Anti-opcat is one Ariel Gabizon. But I outed you. Your choice weighs heavy. But you're a Zcash enthusiast, so I don't know if Satoshi maximalist. Okay.
Increase the block size. Increase the block size.
So, like I said, this session is dedicated to the interaction between SNARK, zero-knowledge proofs, and the world of Bitcoin. And I'm very happy to have Robin with us to talk about BitVM. BitVM has, as we speak, a little over 2,500 enthusiasts watching closely what's going on in the development of this technique, with thousands and thousands more that are lurking silently and trying to see when is this going to production and adopted. So I'm very eager to hear what you have to present to us.
Thank you. Yeah, I'm Robin Linus, and today I'm going to talk about BitVM, which is a way to enable smarter Bitcoin contracts. First of all, the motivation. We would love to scale Bitcoin to 1 billion users and beyond. And that has been more or less the dream since the beginning. It hasn't been fulfilled yet, and BitVM is an approach to get closer to it. First of all, in the long run, most users probably won't be able to afford main chain fees. We would have to significantly increase the block size to make everyone be able to afford main chain fees, but that would harm decentralization, so we will probably not increase block size to like gigabytes or something. So most users just won't be able to afford main chain fees in the long run, and that means we would love to have some kind of side systems like side chains, ZK rollups, or stuff like ZK coins, which is another layer 2 protocol. And yeah, we would love to enable rapid innovation. We just heard in the last talk that it's hard to change the base layer, but on second layers we could have rapid innovation and cheap experimentation. And in that ideal world, all these L2s could be interconnected via the Lightning Network, and then we could scale Bitcoin very well. However, the big problem is, how do we build better bridges? How do we bridge BTC to side systems in a trustless or trust-minimized way? Currently, the best we can do is just multi-sigs, which is, of course, not very satisfying. BitVM enables that, and it does so in like the stack is roughly, first there's a hack to introduce state into Bitcoin. That gives us stateful scripts, and on top of these stateful scripts, we can build the BitVM, and on top of BitVM, we can build bridges. So that's roughly the stack, and it's also roughly the outline for my talk. First, I will talk about stateful Bitcoin scripts. The key idea behind BitVM is to introduce state using signatures. The rough idea is that if we could somehow sign a value, like an arbitrary value, currently we can just sign transactions, then we could use that signature to enforce the same value for like a variable, let's call it x, in script 1 and in script 2. And the way we do that is, let's say Alice, she signs that x has the value 42, and script 1 forces her to reveal a signature for the value x, and she sets it to 42. And then anybody else, for example Bob, he can use that signature in script 2 to set the value of x to 42 by just using Alice's signature. And he cannot set it to any other value because he cannot forge a signature for Alice. And yeah, Bob could be anyone. Like, there is no need to specify Bob in the beginning. Alice just publish some signature, and then anybody can use that signature to execute script 2. The big problem is, how do we sign a value, or like, how do we check the signature for a value? Because currently we don't have check sig from stack, which is a proposed opcode to check arbitrary signatures in Bitcoin script, but currently we don't have that. And that's the key problem. And the solution for that is Lamport signatures. Lamport signatures are conceptually very simple. They require only hash functions, and that means it's possible to implement them in Bitcoin script as it is today. And the main drawback of Lamport signatures is that they're incredibly large. They're a super simple concept, and the way they are structured actually makes them very large. But still, it is possible to do useful things with them. We can sign bytes, we can sign 32-bit words, and we can sign like hashes, and it is clunky, but it works. Here's an example for a 1-bit message in a Lamport signature. It's the logging script, and what it does, it expects a pre-image on the stack, and then first it hashes the pre-image, then it duplicates it, then it compares it to a hash 1, and then it compares it to a hash 0. And if one of them matches, then it leaves the value on the stack. Like if you provide pre-image 1, which hashes to hash 1, then this script will leave 1 on the stack. If you provide pre-image 0, which hashes to hash 0, then this script will leave 0 on the stack. And if you provide an invalid pre-image, then the script will just fail. And this is the heart of it all. Like, this is really the key idea. Once we have 1-bit Lamport signatures, we can just copy that script n times to get an n-bit Lamport signature. And here you can also see why it's large. It contains, like the public key in Lamport signatures are these hash 1 and hash 0. And both of them are, here they are 20-byte hashes, so we already have 40 bytes just for the public key, and then another 20 bytes for the pre-image. So we are roughly at 60 bytes per bit. We can optimize that a bit with Winternet signatures. That gets us down to like 25 bytes per bit, but it's still quite large. And that's what makes BitVM so clunky, actually. There's a second way to introduce state. We are using both because they are useful in different situations. And this is called connector outputs. The rough idea here is that I have some parent transaction, and in particular a conditional transaction, and the conditional transaction has a condition transaction. Do I have a pointer here? No, it doesn't work. And the idea here is Bob can execute the conditional transaction if he also executes the condition transaction. So Alice essentially says, hey, you can have my money if you execute the condition transaction. And the thing how you introduce state here is that if whatever alternative transaction, if that spends the connector output, then that renders the conditional transaction obsolete and it's impossible to execute it. Because Alice pre-signed the conditional transaction and she committed in her signature to both her own input, but also to the input of the condition transaction. But if it's spent in another transaction, then the conditional transaction cannot be spent. And this is another interesting way how we can introduce state in Bitcoin script. And we are using both of them in BitVM. Now, rough overview of the BitVM architecture. The paradigm in general, it uses optimistic computation. So all of the expensive, clunky stuff is only ever needed in case of a dispute. In the happy path, the prover just makes a claim, and if that claim is correct, then nobody will dispute it. And then it's just a simple transaction on the chain, and nothing fancy happens. Only in case of a dispute, we have to roll out all these complex things and essentially run BitVM on chain. And in general, it never runs the computation itself. It only ever disproves a faulty execution. So the prover makes a claim that some state is the correct result of a transition. And if that is incorrect, then we try to succinctly disprove that instead of computing the correct result. Because disproving is much simpler. I think That's a common technique in the ZK world. Yeah, and then we build a SNARK verifier on top of that, and that essentially gives us universal computation and allows us to more or less verify any function. We have built like an advanced version of Bitcoin script, or like a meta language on top of Bitcoin script. And yeah, that allows us to express more complex Bitcoin contracts. And yeah, it's essentially a templating language for script. Script is very limited. It doesn't have loops and stuff like that. So for example, we have just some syntactic sugar to unroll loops and to parameterize loops and to compose functions and to compose them into more complex things. Then we have a set of opcodes that we provide in that language. For example, bitwise XOR, bitwise shifts, but also like hash functions like break3. We have heard in the talk before that we cannot concatenate bytes on the stack. So what we are doing is that we just represent byte strings as like single bytes on the stack. So if we have like a 20 byte string, then we have 20 stack items instead of one stack item that is 20 bytes. And using that representation, we can concatenate bytes, of course, because we just put them together on the stack. And yeah, we have implemented our own hash functions on top of that to then be able to introspect the data that we're actually hashing, which is not possible with the existing opcodes. Yeah, and also we have implemented field arithmetic to implement our SNARK and our SNARK verifier, and I'll go into that in more detail later. Yeah, and then we have primitives for statefulness, essentially Lamport signatures with like a nice API that allows you, or like that gets you away from the scripts that I showed you, so that you don't have to write these scripts for every value that you want to use. You just use like a high-level opcode, and that makes it like much easier and allows you to tame the complexity. And yeah, like a nice API for connector outputs. And yeah, that is roughly the overview of our language. And this allows you to express potentially very complex scripts and also put them in complex trees. Tap tree, or like the taproot update that allowed us to commit to. Like previously, it was just that every output had a single unlocking script, and taproot, the taproot update allowed us to have like a Merkle tree of scripts, and then you can have millions of scripts, and you just have to satisfy one of them, and that allows you to express much more complex spending conditions. Yeah, and then we put these transactions and scripts into graphs of transactions. So the language is not just scripts. It's scripts in the context of graphs of transactions, just like I showed in the previous slide with the connector outputs. Now, how do we build bridges with that? In general, the idea is how can we bridge BTC to any other system? And the rough idea is, if we had just some kind of bridge, even if it would be clunky, that would be already very useful, because it is okay if the bridge is only used rarely and only for large amounts, because regular end users, they can just use cross-chain swaps. The bridge in itself is mostly a guarantee that this wrapped BTC on the sidechain or in the side system has a guaranteed value. So whatever happens to the side system, you can always get the actual BTC value back on the main chain in case of an emergency or whatever happens. And that gives a trustworthy value for the wrapped BTC. And this is the main reason, or like that's the main use of the bridge. And it is very useful even if it is clunky and very slow. Yeah, cross-chain, I mentioned already, end users will mostly use cross-chain swaps and ideally via Lightning, so that it would be absolutely instant and more or less frictionless, cheap in particular. Yeah. The main limitation of BitVM is that it requires some set of operators that you have to define during setup. But in our current version, everyone can be a verifier, which gives you quite strong security guarantees, because even if all the operators are malicious, they are not able to steal money. Now I'm talking more about the guarantees. Yeah, it's a federation, but a single honest member suffices. In the setup, we can have up to 1,000 co-signers who sign the graph. And then we have like roughly 100 bridge operators. And the guarantees are that the bridge is safe as long as one of the 1,000 co-signers was honest and deleted their key after the setup. And that means nobody can steal any deposit. And the bridge is live as long as there is at least one honest operator that processes peg out. And the good thing is also you can become a member. So if you're a liquidity provider or an exchange or whatever entity that has a big stake in the site system, they can become part of the setup ceremony, or they can even become a bridge operator. And for themselves, then it's completely trustless because they trust that they are honest. Here is like a dummy idea of how the bridge works, roughly. It's more complex in practice, but this shows like the rough mechanism. Here we have Alice pegging in 100 BTC, and then she sends it to an N of N multisig, and this multisig pre-signs. This is part of the setup. This is the 1,000 co-signers that I talked about. They pre-sign a peg out transaction, and this peg out transaction just gives the money to the operator. And this signature, it commits to 2 more inputs, to the 2 inputs from the kickoff transaction. And the first input is just a delay. Like it just says 6 months after the operator executed the kickoff transaction, they can execute the peg-out transaction. So they have to wait. This is essentially the dispute period. And the second one is the connector output. And that connector output, that is also pre-signed by the operator for the slash transaction where the connector output can be burned. And it can be burned exactly if the operator loses the BitVM game against some of the watchtowers. And this essentially says, when the operator witnesses a valid peg-out, they execute the kickoff transaction, and then they hope that nothing happens to their connector output. Of course, nothing happens to their connector output if they have been honest. But if they have been dishonest, then somebody will challenge them and win the BitVM game, and then the winner of the BitVM game will win an output that allows them to execute the slash transaction, and then the operator will not be able to touch the funds. Since we assume there is always one honest operator, there will be some operator that doesn't lie, and then they will execute the peg-out transaction. A vast simplification here is that the money just goes to the operator. Usually we have some Bob or something, like some arbitrary user who wants to peg out, and actually we want to give the money to Bob. Here, in this simplified version, we just give the money to the operator, but this is just a simplification for the sake of the argument. In the next slide, I try to explain how to give the money to Bob, actually. And yeah, how do we build a SNARK Verifier in script? Well, first of all, we are using a pairing-based proof. Essentially, we are using Flonk. And they're constant size, but still constant can be quite large. Implementing it in Bitcoin script still takes like gigabytes of data, or like gigabytes of script. And the script size limit is 4 megabyte, or like a full block. We can have at most 1 block of script. So how does that fit together? How can we fit gigabytes of script into a block that is at most 4 megabytes? And that is the key idea of BitVM 2, which is, well, we just make a commitment to 1,000 intermediate results. For example, if we want to compute f of x equals y, we cannot compute f because f is way too large. So what we do is we chunk it up into 1,000 chunks, like f1, and f1 maps x to z1, and then f2 maps z1 to z2, and f3 maps z2 to z3, and so on and so on, until f1000 maps z999 to y. And all these FIs, they can be much smaller, for example, 4 megabyte each, and disproving a single step suffice. Like the operator, they claim, they make a commitment to like all these ZIs, and if any of these steps is incorrect, then you can execute that step and compute the correct result and show that the correct result is different than what the operator claims, and that disproves the operator. Yeah, for example, here, if f42 of Z41 is not Z42, then you would execute f42. And yeah, every FI can be up to 4 megabytes, and in total that gives us 4 gigabytes of script. And that is roughly enough to implement a SNARK verifier. I'm glossing over a couple details here, but that is the rough idea how we can execute gigabytes of script in just a single block, or how we can verify gigabytes of script in a single block. So this is a more realistic setup of the bridge. It is kind of similar, like we have the pack-in transaction, and here's the take transaction that gives the money to the operator. First of all, the trick how Bob gets the money, like Alice is the person who packs in, Bob is the person who packs out, and Bob burned his coins on the sidechain, and the operator witnessed that, and now the operator gives his own money to Bob. Just independently of the rest of the setup, the operator gives his own money to Bob. And everybody can witness that in the chain, and then everybody can see that Bob is actually entitled to take the money out of the bridge, because everybody saw the valid pack out of the operator, and everybody saw the valid pack out of Bob, and everybody saw that the operator actually gave Bob his money. And then we have a very similar setup as in the slide before. Just here it's a bit different. It works such that here you see connector output A. The connector output A is pre-signed by the operator with SIG singer, anyone can pay. That means the operator only signs his own input and a particular output, and he essentially says, everybody can have my connector output if you give me 1 BTC. And this is because the operator should be paid the fees that he needs to make to execute the assert transaction if he is honest. And yeah, like everybody can buy the connector output of the operator and force the operator to go down the unhappy path. And in that unhappy path, the operator has to execute the assert transaction, and in the assert transaction, they have to commit to all the intermediate values. And then there is a dispute period of 2 weeks, and if any of the assertions was wrong, then you can execute one of the intermediate functions. For example, here f42, and that disproves the operator, and it takes it burns the connector output C, which renders the take-two transaction obsolete. So then the operator cannot touch the funds at all. Yeah, that is the rough overview of how the bridge works. The limitations, first of all, complexity. Right? It's very complex, like the scripts are very complex. Implementing a SNARK verifier in this clunky Bitcoin script language is highly complex. It takes gigabytes of script, as I said. And the other thing is we have to balance the incentives. So it should always be such that the loser pays the winner's fees. So if the operator is dishonest, then the operator should pay the fees for the verifier that disproves them. However, it's hard to estimate it, because during compile time, like when we set up the contract, we have to set the fees in stone, and we cannot change them later on. And if the fees change too much, then it might turn out that it is too expensive to disprove the prover. And yeah, then the system would break. So the incentives have to be balanced. So we have to estimate the fees correctly, or we have to overshoot the fees so much that in practice they will never go that high. And yeah, that is definitely a capital cost to the system. The next one is, sure. Like if the incentives are balanced, then the chain is not needed. That's the good thing. Like as long as the incentives are balanced, and if it's guaranteed that you lose money if you lie, then you probably won't lie in practice. And other optimistic systems have shown that this actually works out in practice quite well. Yeah, the operator has to front the capital for that peg out every 2 weeks. For 2 weeks, not every 2 weeks. So when a peg out occurs, then the operator has to front the capital for that particular peg out. Some people thought that the operator has to front the entire capital, the total value locked. That is not true. It's just the capital for that one single peg out that has to get fronted. And yeah, only for 2 weeks. And of course, the operator can cycle back the liquidity. Like he can process, let's say a lot of peg outs happen at once and the operator doesn't have enough liquidity, then the operator can just process one by one and take the liquidity back after each peg out. Because he gets the money that he fronted, of course he gets it back. And yeah, the other thing is like you can incentivize the operator to prioritize you by paying a higher fee to the operator. Yeah, but the good thing is no one-to-one collateral is required. There exist already bridges for BTC, but they require one-to-one collateral or even a higher collateral. Here we don't need any collateral more than the fees. So the collateral is just a function of the fees and not a function of the total value locked. And yeah, another big drawback is that for every peg-in, all these 1,000 co-signers have to pre-sign about 100 peg-out transactions, one for each operator. And yeah, another issue is that these co-signers, they can censor peg-ins. They can just refuse to sign and then you cannot process the peg-in. But they cannot censor peg-outs, which is the important part, so nobody loses money. Summary and outlook. First, yeah, BitVM enables smarter Bitcoin contracts. The use case is mainly trust-reduced bridges for L2. For L2s, I have not seen any other valuable use case except for bridges, but once we would have bridges, we could essentially build everything else because we can build like an EVM-like sidechain or something, which then would enable stuff like AMMs and these things that people would like to build. But it's not possible to do that directly on BitVM because BitVM is just way too clunky, but it would work for bridges very well. Yeah, BitVM is practical, but it is clunky, as I just said. But the great thing about it is, of course, it requires no soft forks. Jonas mentioned it in his talk. It's hard to get consensus. Bitcoin changes rarely, and yeah, BitVM is a hack to get around that, essentially. However, it would be great if we had some other opcodes, for example, TX-hash. TX-hash would be great. It's a covenant proposal, and that would allow us to get rid of the trusted setup. So we wouldn't need this trust assumption anymore that we have 1 in 1,000 honest co-signers. We could just have that covenant, and that would guarantee that you cannot break the covenant. Even better would be opmal. Jonas already mentioned it, our current implementation for feed element multiplication. He mentioned the integer multiplication, like the large integer multiplication, but the feed element multiplication is like roughly 150 kilobytes or something. With opmal, we could reduce it drastically, maybe just to a couple bytes even. Yeah, and block hash would be great for blockchain introspection. We completed a draft version of it, and hopefully we will have like a reckless mainnet by the end of this year. Okay, that's it. Any questions?
Raise your hand. All right. Can you hear me?
Hello. I see there one slide mentioned that there are 1,000 cosigners. Is it needed for all these 1,000 cosigner participate in one signing process?
Yeah, you would run like once or twice per year or so. You would run that setup where new people can peg in.
Is it using threshold signature?
Yeah, you would use music to like compress these 1,000 signatures into a single schnorr signatures. Yeah.
Yeah, is it sorry? Is it feasible to do it? Because the parameter I usually see is 2 out of 3, 5 out of 7, usually below 10. Is it would it be feasible to do this 1,000?
Jonas told me, like Jonas is the main author of the Music 2 paper, and he told me that at least computationally it is feasible. Of course, it is a problem of how to coordinate that, because if a single cosigner fails to sign, then of course it all holds. But yeah, you can incentivize people to actually show up with like providing some deposit or something to become a cosigner in the first place. But yeah, that's definitely an issue.
Do you have timelines for starting to see, a realization of this on a testnet, or?
Yeah, like hopefully by the end of the year we will have like a reckless version, a mainnet
version.
Yeah, like the first Lightning version was called the reckless version.
Awesome.
And in that tradition, we would like to create a reckless BitVM version within, by the end of this year, hopefully.
Amazing.
Are you able to add additional people to the threshold signature after the initial ceremony, or is it locked in and that's it? And if someone, I guess, loses their, if key gets compromised, they would just be slashed, but can you add extra people to it?
No, it's just one-time setup. Like these 1,000 people come together, they create a signature, and then they even want to delete their keys. Like this is considered honest that they delete their key.
Sorry, I meant more like the bridge providers.
You might mean the 100 operators.
Yeah.
Yeah, actually not. No, if these cosigners are honest, then they delete their keys, and then it won't be possible for them to add another operator because they would have to sign another signature. Yeah.
Anyone else?
But maybe I should mention that these operators can be thresholdized. So the operator doesn't have to be a single key; it could be a federation, and like it's just abstracted away from the rest of the system.
Okay, thank you, Robin.
Thank you.
So I must mention that Robin's talk is an invited talk because we thought it would be amazing to have, next to the papers that were submitted papers, also complement with invited talks about the topic.